Now it's time for one of my favorite topics in Physics 6, which is understanding orbital motion and deriving Kepler's third law of orbital motion for circular motion, for circular systems. So Kepler discovered three laws that govern the motion of orbits, and they're more general than what we're going to do in Physics 6 because they apply to elliptical orbits as well as circular. But we can understand what's going on in circular orbits using just the tools we've learned in Physics 6, namely Newton's second law, Newton's law of universal gravitation, and the expression for centripetal acceleration. And with that, we'll be able to analyze the motion of the moon in its orbit around the Earth. We'll be able to study satellites, and I think this is kind of a culmination of all the cool stuff that we've learned in the mechanics portion of Physics 6. So let's see how all this works. I'm going to consider an example of a satellite orbiting planet Earth. So here's Earth, there's the center, and this is a poorly drawn satellite. Maybe it's communications, maybe it's broadcasting TV or something. So this satellite is a distance r from the Earth's center. Let's draw a free body diagram for the satellite. The coordinate system I'm going to use has a radial direction pointing toward the center of the Earth. There's only one force on the satellite. It's just the force of gravity. So with gravity, you can kind of think of it as being like a string that's holding this satellite in place. And that satellite is getting spun around the center of the Earth by this string that's holding it. So that gravity force kind of plays the role that a tension force would, except there's not actually a string there. This is a field force. The objects aren't in direct contact, but even so, this satellite's getting held in its circular orbit by that centripetal gravity force. So, Newton's second law in this radial direction reads sum of the forces in the radial direction equals mass times centripetal acceleration. We've just got one force, it's the gravity force, and we have our centripetal acceleration v squared over r. And remember, according to our sign conventions, if the force is directed toward the center, that's considered negative. If it's directed outward, that's considered positive. This force is toward the center of the circle, so we give it a minus sign. And that centripetal acceleration also gets a minus sign, because it's also pointing toward the center. So those two minus signs cancel out, and it ends up being positive. So we have an expression now, g times mass of object 1, which is the Earth, times mass of object 2, which is the satellite, divided by the distance between them squared. That's just the expression for gravity force, equals m2 v squared over r. On the right hand side, we have the mass of the satellite, which is the object of interest. So those masses cancel out. One of these r's cancels out, and we get a relationship that v squared equals g times mass of Earth divided by r. So right away, this is useful because now we have a formula for the speed of an orbiting object around the body it's orbiting. So if we knew the distance away from the center, we could figure out the speed. This is pretty interesting. It's saying there's a one-to-one correspondence between the speed of an object in orbit and its radius, or the distance of that orbit. The radius of the orbit uniquely defines the speed. There's only one possible speed for a given radius, and there's only one possible radius for a given speed. Now we can keep going with this equation and relate it to the orbital period, the time it takes to complete one orbit. Because the speed is the distance traveled, the circumference of the circle of the orbit. If you go around the orbit one time, that's a circle of circumference 2 pi r. And you divide by the time it takes to complete one orbit. I'll call that time capital T, which is also known as the period. And now substituting that, we have an expression 4 pi squared r squared over t squared equals g m over r. And usually people rearrange this so that it looks like t squared equals 4 pi squared over g times m times r cubed. And written this way, that's known as Kepler's third law. It's saying that the time that it takes to complete one orbit is related to the radius of that orbit. Square of the time is proportional to the cube of the radius. That's Kepler's third law. In the next few videos, we'll do some examples using these two equations.